Today we're going to be talking about implicit differentiation. And implicit differentiation is used when we can't solve for y. So I just want to review real quick with you guys the meaning behind dy dx. Remember, dy dx stands for when we're taking the derivative of y with respect to x. So when we're taking dx, it's a notation we've never written. That's the derivative of x with respect to x. So a lot of times that's 1, or all the time I should say that it's 1. ds dt, the derivative of s with respect to t. So that's our velocity function if s is standing for position, which a lot of times in calculus that's what s is standing for. And then dv dt, the derivative of velocity with respect to time. So it's important for you guys to realize what those notations mean. These are our steps for implicit differentiation, so please make sure you write these down. You differentiate both sides with respect to x. So remember, when you find the derivative with respect to x, any variable that's not x, you have dy dx if your variable's y, or if your variable's z, it's dz dx. So you collect all the terms with dy dx on one side, factor out the dy dx, and then you solve for dy dx. A lot of times that's by dividing by whatever you just factored out. Okay, our first example. So find dy dx. I'm going to do this one a little bit of a long way. This first step we never really have written. So if I take this first term here, 3x, x to the third, the derivative of that is 3x squared, technically dx dx. When we're taking the derivative with respect to x, of x, it's dx dx. Then we have 3y squared, the derivative of y with respect to x. And then the other side, we have a product rule because we have x and we have y. So the derivative of the first is just 3, leaving the second alone, plus, leaving the first term alone, derivative of the second is dy dx. Now I want you guys to note one thing. I don't need this dx in there. I didn't even write it over here for the second one because that's what we're so used to. So you don't even really need to be writing that. I just wanted to highlight that the derivative of x with respect to x is that notation, that's 1. So I'm going to erase that. Okay, so now what we have to do is we have to get these dy dx terms, anything with a dy dx on one side, everything else on the other. So I'm going to leave the 3x squared on this side, and I'm going to subtract the 3y over to the other side. Then what I'm going to do is I'm going to leave the 3x dy dx. On this side, I'm going to subtract 3y squared dy dx. Now I'm going to factor out the dy dx and get 3x minus 3y squared. Then I'm going to divide by this 3x minus 3y squared on both sides, so that on the right side I have dy dx. On the left side we have 3x squared minus 3y all over 3x minus 3y squared. So this is our implicit differentiation, or derivative of this function with respect to x. Okay, our next example. Analyze the problem real quick first. We don't have any product rules or quotient rules, so I can just go through and take the derivative. Remember, the derivative of 5y squared with respect to x is 10y dy dx. The derivative of sine is the cosine of y, but it's essentially a chain rule because now I have to take the derivative of the y, so that is dy dx. And that equals 2x. Notice how when I took the derivative of x with respect to itself, I just take it like we're used to. Anytime you see a y, you have to have that dy dx next to it. So this one's a little bit easier than the last one because everything with a dy dx is on one side, so I can just go ahead and factor that out. So then I have dy dx is equal to 2x all over 10y plus the cosine of y.
Our next example is the sine of x times the cosine of y equals the tangent of y. On the left side we have a product rule, so we have the sine of x times by the cosine of y, and then we have tangent of y just standing by itself. So for our product rule, derivative of the first, which is cosine x, leaving the cosine y alone, plus, now leaving the first alone, times by the derivative of cosine y, well, that is going to be the negative sine of y dy dx. And that is going to equal the derivative of tangent of y. Derivative of tangent is the secant squared of y dy dx. Now simplifying that a little bit, we have cosine x times cosine y minus sine x times sine of y. Now, for dy dx, I'm just going to put y prime. It's just another way of writing it. Secant squared of y, so we have secant squared y times y prime. I have to get every term that has a y prime on one side. So I have the secant squared y times y prime plus the sine of x times by the sine of y times by y prime. Now I have to factor out my y prime. So then getting y prime, we have the cosine of x times by the cosine of y all over secant squared y plus the sine of x times by the sine of y.
Now our second derivative. The second derivative gets a little tricky. Okay, so you find the first derivative like we normally do. Okay, so I have 3y squared dy dx plus derivative of 3y is just 3 dy dx equals the derivative of this right side with respect to x is just 2. I factor out my dy dx. and then I divide. So that's our first derivative. Now when we take the second derivative, basically when I take the derivative, this, remember, stands for y prime. So when I take the second derivative, I've taken the second derivative of y with respect to x. I have here a quotient rule. Okay, so we have a quotient rule. Low d high, derivative of 2 is 0, minus high d low. The derivative of the bottom is 6y dy dx plus 3. So that 3 goes, or plus 0, so that 3 I don't really need. Draw a line, square the below. Now when we do the second derivative, we can't have this dy dx in there. So what I need to do is I need to substitute back in what we got for our first derivative in here for dy dx. Notice a few things. This first term, just because the example I picked, went to 0. So simplifying that, we have negative 12y. Now I substitute in what our first derivative was for dy dx. Now we simplify, so I can multiply the top together here to get negative 24y. The denominator of this fraction goes in the bottom, so I have 3y squared plus 3 cubed. So that is our second derivative. So the trick is you need to substitute in, wherever you find a dy dx, you need to substitute in for that dy dx what your first derivative was. Find the equation of the tangent line and the normal line. So we want a tangent line, we want a normal line. First job is to find the derivative of this. Okay, derivative here is a little bit complicated because here again I have a product rule because I have an x times a y. So derivative of the first is 1, leaving the second alone. Plus, leaving the first alone, derivative of the second. Should have left myself a little bit of room there. So I have 2x y. Now sometimes instead of writing dy dx, what you could do is you could write y prime, realizing that that's not y to the first power, that's our derivative. So instead of writing dy dx, you can write y prime if you want. So I'm going to be doing that for this example. Now this second term here, this is also a product rule. So derivative of the first with respect to x is 6x, leaving second alone, minus leaving the first alone, so the first one is negative 3x squared. Derivative of y is y prime. Derivative of 4 is 0, derivative of 0 is 0. So remember, this y and that y were your y primes. So I essentially need to isolate those terms. So I'm gonna subtract the 2x y prime over to the other side and add this 3x squared y prime over to the other side. So on the left I would have y squared minus 6xy. On the right we would have 3x squared y prime minus 2xy, y prime, factor out your y prime, now I divide and I get y prime to be equal to y squared minus 6xy all over 3x squared minus 2xy. Now we need to plug in our point to find the actual value of the derivative. So I have 1 minus 6 times a negative 1 times a 1 all over 3 times a negative 1 squared minus a 2 times a negative 1 times a 1. So I have 1 plus 6 over 3 plus 2, that is equal to 7 over 5. Now that I've found the slope of my line, it's just a matter of writing the tangent line. And again, I like to use point slope formula. So y minus y1 equals m times x minus x1. Your normal line has the same point, but the opposite reciprocal slope. So there's your normal line. So there's our tangent line and the equation of our normal line. This next example, finding dy dx. Now this is basically what we've been doing before. Just remembering that when you're finding the derivative of y, that's dy dx. And then as this right side, realizing that you have a bunch of chain rules in there. We have, bring down the 5 halves, we're left with a sine of 3 over x, reduce this exponent by 1, so that's 3 halves, times the derivative of sine, which is cosine, times the derivative of 3 over x. Little sidebar, 3 over x is the same thing as 3x to the negative 1. So the derivative of that would be negative 3x to the negative 2. And I'm okay if you guys leave it like that. Okay, that's it for today. Please make sure your lesson summary is submitted on time.